This video is brought to you by mywayteaching.com.
In this particular part, we are going to study about the variation of pressure with the depth. Okay, you just consider this fluid inside this beaker. It is at rest in this container. Okay, this fluid is at rest in this container. Okay, point one, you can see here. This is the point one, and this is point two. Okay, point one is at a height h above point two, isn't it? It is at a height h. The pressures at point one and two are different because they are at different heights. So the pressure at point one we'll consider it as P1. Okay, and we'll consider pressure at point two as P2. Okay, consider a cylindrical element of fluid having a area of base A and height h. Okay, this is the element that we have considered, cylindrical area having the base A and height h. As the fluid is at rest, the resultant horizontal forces should be zero and the resultant vertical forces should balance the weight of the element, isn't it? So this horizontal force, the resultant horizontal force must be zero since the fluid is at rest, and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical directions are due to the fluid pressure. Okay, so the forces which are acting here, you can see vertical direction are due to the fluid pressure, and at the top it is P1A acting downward, and at the bottom it is P2A acting upward. Okay, here it is P1 into A, and here it is P2 into A. Here it is acting upward, and in the top it is acting downward. If mg is the weight of the fluid in the cylinder, then we can write P2 minus P1 into A is equal to mg. Okay, now if rho is the mass density of the fluid, we have the mass of the fluid is that mass of the fluid is given by rho into v, isn't it? In other words, we can write v as h into a, so that we can write P2 minus P1 into A. In place of m, we'll substitute rho h a into g. This a This A get cancels and we get P2 minus P1 is equal to rho Hg, isn't it? Yes. Pressure difference depends on the vertical distance h between the points 1 and 2. Okay. And the mass density of the fluid rho and acceleration due to gravity g. So this pressure difference, it depends on all these 3 points. Pressure difference. So this pressure difference, it depends on the vertical distance h between the points 1 and 2, and even it depends on the mass density. Not only these two, it also depends on the acceleration due to gravity. Okay. We know acceleration due to gravity is represented by g. If the point 1 under discussion, if it is shifted to the top of the fluid, say on the water, here on the top of this fluid, if it is shifted there, which is open to the atmosphere, P1 may be replaced with atmospheric pressure PA in that case. So we replace P2 by P in that case. Okay. Then we can write the equation as P is equal to PA plus rho GH. Okay. This is the new equation. Thus, the pressure P at a depth below the surface of the liquid open to the atmosphere is greater than the atmospheric pressure by an amount rho GH. Okay. The excess pressure, that is P minus PA, which is given by rho GH. This is the excess pressure, right? So this excess pressure at depth h is called as gauge pressure at that point. Okay, this excess pressure is called as what? Gauge pressure at that point. Okay. The area of the cylinder is not appearing in the expression, that is P is equal to PA plus rho GH. Thus, the height of the fluid column is important and not cross-sectional or base area or the shape of the container. So from this equation, one thing is clear, that here it is not having any area expression or the area term in this. So height is very much important, not the shape of this container. Okay. The liquid pressure is same at all the points at the same horizontal level. That is at the same height, or we can say at the same depth. The result is appreciated through the example of hydrostatic paradox. Okay. What is this hydrostatic paradox? You just see in this illustration. Consider three vessels A, B, C of different shapes. See, A is of shape B, and B is the of different shape, and C is of different shape. So they are connected at bottom by a horizontal pipe, isn't it? This is the horizontal pipe. So they are connected by that pipe. On filling with water, the level in the three vessels is the same, though they hold different amounts of water. So when you fill water, you one thing you will observe that the levels of water in all these three different vessels will be same even though they hold different amounts of water because they have different shapes. This is because water at the bottom has the same pressure below each section of the vessel. Why they are at same level means water at this bottom is having the same pressure. That's why. Okay, that is the reason. Here pressure plays a important role. Okay, so now let us solve a simple problem. The problem is what is the pressure on a swimmer 10 meter below the surface of a lake. So if it is a lake, the swimmer is 10 meter below the surface of the lake. Okay, then what is the pressure? So they have given H here, isn't it? That H is 10 meter. And we know rho is given by 1000 kg per meter cube, and we can consider g as 10 meter per second square. So we know the equation when okay on the surface of the water the pressure is pa and the excess pressure or the gauge pressure is rho gh. So this pa is having a standard value that is 1.01 into 10 raised to 5 Pascal, and the density is 1000 kg per meter cube. G is 10 and H is 10 meter. So if you simplify this, we get 2.01 into 10 raised to 5 Pascal. Okay, this is, in other words, we can express in terms of atmosphere, that is 2 atmosphere. Okay, this is 100% increase in pressure from surface level. At a depth of 1 kilometer, the increase in pressure is 100 atmosphere. Submarines are designed to withstand such enormous pressure. As we go deeper and deeper, that pressure will increase enormously. Okay, so the devices should be designed in such a way that those devices under the water should able to withstand that enormous pressure. Even submarines are also designed in such a way so they are able to withstand that uh, you know uh, pressures of hundreds of atmosphere. Okay, now let us study atmospheric pressure and gauge pressure. We already know this gauge pressure and atmospheric pressure. This gauge pressure is the pressure, that excess pressure. Atmospheric pressure is at the surface we get. Okay. The pressure of the atmosphere at any point is equal to the weight of a column of air of unit cross sectional area extending from that point to the top of the atmosphere. Okay, weight of the column of air of unit cross sectional area from where we are considering that object or the point to the top of the atmosphere. At a sea level it is 1 atmosphere, which is given by 1.013 into 10 raised to 5 Pascal, isn't it? This is the pressure at sea level. Italian scientist, that is Torricelli, devised for the first time a method for measuring atmospheric pressure. How he did that? Yes, he conducted an experiment and then he found the method for measuring the atmospheric pressure. What he did, let's see. See, he first of all he took a long glass tube closed at one end and filled with mercury is inverted into a trough of mercury. You can see that in this figure. So a long glass tube, he took a long glass tube which is closed at one end, and it is filled with mercury and it is inverted into a trough of mercury. This device is known as a mercury barometer. So the space above the mercury column in the tube contains only mercury vapor whose pressure P is so small that it may be neglected. Okay, here in this space above the tube, okay, in the tube, the space above the mercury column in the tube contains only the mercury vapor, and that pressure is very small, and even we can neglect that. The pressure inside the column at point A must be equal the pressure at point B, which is at the same level. So pressure at B is equal to pressure at A, that is atmospheric pressure. We can call it as atmospheric pressure. If we consider two points which are at the same level, then the pressure at those points are equal. So we can see pressure at B is equal to atmospheric pressure, which is equal to pressure at A. A and B are the 2 points which are considered at the same level. So PA is equal to rho GH. Okay. Where rho is the density of mercury and H is the height of the mercury column in the tube. So in this experiment, it is found that the mercury column in the barometer has a height of about 76 centimeter at the sea level, which is equivalent to 1 atmosphere. So this can also be obtained using the value of rho in the equation, and that is PA is equal to rho GH. Okay. A common way of stating pressure is in centimeters, so in terms of centimeter or of mercury. Okay, a pressure equivalent of 1 is called as torr. That is 1 torr is equal to. It's a method of measuring the pressure. We'll express like this: 133 Pascal. Okay, the of Hg or torr are used in medicine as well as in physiology. In meteorology, a common unit is bar. So in different fields, we use different units to measure this pressure. So 1 bar is equal to 10 raised to 5 Pascal.